Okay, hello everyone. Good morning, all of you. Take every chance you get in life because some things only happen once. And today's quote is: Your talent is God's gift to you, and what to do with it is your gift back to God. Okay, we are given so many talents. Many times we don't recognize them, right? We are having so many gifts. Okay, why we call it as gift? Feel it as actually natural, but it's not natural. All people are not having your gifts. Suppose you can see everything well. There are many people who cannot see, and you can listen, you can speak well, and there are many people who cannot speak and listen. And you can do everything with your hands and legs, and there are many people who are handicapped and who cannot do everything by themselves. And you can think, and many people who cannot think also. There are only many people who are mentally challenged, and we have so many gifts, but only small thing if you don't have, we will curse God. We never thank God for whatever we have got. We always see whatever we don't have. We never appreciate whatever we have and how we use them. Right? These gifts are we have to use them, and we have to make God happy because He should feel that it's worth it. Okay, to give you those gifts. Okay, and today is the birthday of Abraham Louis Breguet. He is a horologist, means actually watchmaker, right? And inventor who became the leading French watchmaker of his time because of his artistic as well as technical skills. His innovations include a self-winding watch in 1780, the gong spring, which decreased the size of repeater watches, and the first anti-shock device, or parachute, which improved the reliability of his watches while making them less fragile. In 1775, he founded the Breguet watchmaking firm. After 2 years, 2 year interruption during the French Revolution, he continued business with more inventions. He sold the first modern carriage clock to Bonaparte, Napoleon Bonaparte, and created the tact watch by which time could be read by touch. Okay, there are so many innovations in that particular field by Breguet, but just innovation of or invention of a watch is not so simple because it contains so many parts, so many mechanisms and all. Okay, today we will have CFD overview. Okay, so this gives the overall complete whatever we are going to cover in the whole semester. So we'll have the complete overview in this class. Okay. So I'll give you an algorithm like thing like program development or software development methodology. I have given a algorithm like stepwise procedure. In the same way, we'll have a stepwise procedure for CFD. So that is some algorithm like thing, CFD analysis process. Okay, first we have to select a real world problem. Okay, this is one of the main thing. Many times in PhD, people say if you select the problem, half the problem is solved or half work is over because selection of the problem itself is a big thing. And in projects also, when you do final year project and all, first selection of the work. If guide gives you problem, there is no difficulty. But if he says, okay, you search for a problem, it will be really tough thing, right? You have to search and you have to see because there are many things so you have to check because first you have to see whether it is feasible or not. And then you have to see what is the time it will take, because you have a particular limited time you to complete the project or the problem. So you have to see whether that can be finished in the given period. And other thing is whether the resources. Okay, here I have given those things. And okay, selection of a real world problem, and then understand the physics of the problem. Okay, once you select it, you have to understand the physics of the problem, and then check the feasibility and resources of the problem. Okay, these are the main things initially you have to see whether it is feasible or not, whether the resources available to you are sufficient or not, whether the time, even time is one of the resource. Okay, so time also whether it is sufficient or not. These things you have to understand. Okay, first of all, where to search for the problem. I already have given you some of the sources. So again, just I will give you the sources. And one is useful websites are there, and one of the best website is cfdonline.com. Just I will show you. It will contain so much of information. So this is cfdonline.com. Everything related to CFD in the whole world, right? It is completely compiled here. So it's a very, very useful website. So it has CFD news and announcements. So wherever there are conferences and those things, you will have that idea. And CFD Wiki, it's a complete theory related to CFD is there in CFD Wiki. Okay, just if you click here, you'll have reference section, special topics, application areas, and best practice guidelines, validation and test cases. Because if you written a code, so you have to validate it, and there should be some benchmark problems. Those benchmark problem results also you can have here. And the open source section, codes, some of the codes are available, and source code archive, and history of CFD, and so many things are there. And here on the complete theory like fluid dynamics, turbulence modeling, numerics, meshing, cavitation modeling, non-equilibrium flow. And in the special topics, we have acoustics, combustion, parallel computing, turbulence, and transition to turbulence, and shape design optimization. All these things in detail they are there. Actually, it is still developing. Some of the topics are given wide description, but some of the topics still they are to be developed. It is in a development stage. Okay, so many things are available. And CFD jobs database, CFD events calendar, online tools, CFD online discussion forums. So if you have any difficulty and if you have stuck up somewhere and if you don't have help nearby, then you can go to the discussion forums. And CFD resources online, CFD books guide, and so many things are there. Everything is there in CFD online. Okay. And so other useful websites like every package that we have, like ANSYS, Fluent, Flow 3D, CD Adapco, CFD Review, and these are various websites in which you can get what are all the various problems solved with those packages, and what are the types of problems you can do. So such things you can get from these websites. And not only that, the best things are books on CFD. This already I have given you, and also the journals. There are so many journals are there, like International Journal of Computational Fluid Dynamics, International Journal of Numerical Methods in Fluids, Theoretical and Computational Fluid Dynamics, Computers and Fluids, Journal of Computational Physics, Numerical Heat Transfer, Journal of Turbulence. There are so many journals are there which has the problems solved by CFD. So these things, if you go through some of the problems, you can see, and you will have idea what type of problems are solved. And if you have a particular interest and something maybe inspiring you, and uh, you may feel that this particular area may be interesting, then you can choose that particular area. And once you do that, one paper, if you get, there will be cross references will be there, and using those references you can search for the further information and all. Okay, so that's the way we have to go about selecting a problem. So these are various journals and the commercial packages that are available, right? Okay, then you have to understand the physics of the problem. And once you understand the physics of the problem, you have to do the get the model, mathematical model. Okay, so formulate the flow problem. So you have to know what are all the governing equations. So governing equations already you have idea. So we already have seen that the first one is conservation of mass, which is also called continuity. So as I was telling why it is called continuity equation is, okay, before going to that, actually I wanted to give you some, okay, maybe in the next class, while talking about governing equations, we will talk about it. Okay, conservation of mass and then conservation of momentum, which is second law of Newton. Okay, so this is the balancing of forces, and if I have a 3D based on whether it is 1D, 2D, or 3D, you will have a number of equations of motion. Okay, so usually if it is 3D, you will have 3 equations. So the balance of forces in all the 3 directions, x direction, y direction, z direction, you will have 3 equations. And if you have 3 components, u, v, w, right? And then conservation of energy. Again, it is from first law of thermodynamics. Okay, so this is basically equation with temperature as the variable. And conservation of mass also actually the equation of equation with density as the variable. Okay, so these are the basic equations, and if you have like combustion and all, there will be chemical reactions and those things will be included, but these are the basic equations. And if you see, as I was telling, there are what are called as primitive variables. Primitive variables or flow variables. These are density, velocity, temperature, and pressure. Okay, so a problem is said to be closed only if number of equations equal to number of unknowns. Okay, so how many are the number of unknowns?
6.
6 unknowns. And what are the equations? Conservation of mass, 1 equation. Conservation of momentum, 3 equations. And conservation of energy, 1 equation. Only 5 equations. What about the 6th equation?
We will be requiring boundary conditions.
No, that will not come into the governing equation.
Okay, sir.
And if you see here, so this has got density as the variable, and momentum is got velocity as the variable, and energy is the temperature as the variable. Actually, there should be some equation for pressure. Though pressure is there, actually pressure should be there, get another equation, and that is equation of state. Okay. So which relates P, rho, and T. So this completes 6 equations. Okay, and in addition to that, if momentum equation contains viscosity and energy equation contains thermal conductivity. So we have to know these values. If they are constants and if you can get from these values from any data book, so these are no more variables. But if mu and k are not constants, then we should have, because usually they are functions of temperature. Mu is equal to mu of temperature and k is equal to k of temperature. Like that, I have to have relations. These are called as property relations. Like this. Okay, so the problem will be complete. Okay, so closed, we call it as closed. So we can solve the problem. So these are all the equations, and all the equations are called as Navier-Stokes equations. Okay, when we study fluid mechanics, so momentum equation itself is called as Navier-Stokes equations. But in CFD, all equations together, we call them as Navier-Stokes equations. Okay, so that is important.
Sir,
Yes.
sir, in momentum equation, the pressure term will come, no, sir.
Pardon?
In momentum equation, there is a pressure term, right?
Yeah, pressure term is there.
And we
Pressure,
said that
yeah,
we need.
in energy energy equation also, see, pressure term will be there, density term will be there. In the energy equation also there will be pressure and density. Okay, here, okay, later I will tell you what are called as there is what is called as time marching method. I will just go to it a little briefly. So if you see momentum continuity equation, it will be like dou rho by dou t plus del dot rho v equal to 0. Okay, and if you see momentum equations, it will be like dou. Okay, I'll write dv by dt. Okay. Something like this. And if you see energy equation, you will get dou t by dou t plus, okay, something like this. And if you see here, there will be time derivative of density, time derivative of velocity, and time derivative of temperature will be there. So I can, it is, when you discretize, what I do is, I will write this as rho n plus 1 minus rho n by delta t, like this. That is new value minus old value by delta t in a time step. And okay, all the other things I will take it to the right side. And all these things I use old values, so that I can write this as rho n plus 1 is equal to rho n plus delta t RHS of n like this. So that if I have some old value, approximated value, I can update this and I can get the new value. So I can update the density using the continuity equation. And I can update the velocity using the momentum equation. I can update the temperature using the energy equation because I have time derivative. Using the old values, I can find out what are the things in the future. So I can march in time. Am I clear about it?
Yes, yes, sir. It's clear, sir.
So this is what is called as time marching method. So it is easy to solve density from continuity, velocity from momentum, and temperature from energy. And though I have pressure here, it is there. Here also on the right hand side, there will be some pressure terms will be there. Okay, I'm not writing those things. And so this is the way normally we solve. And so I need a new equation. Anyhow, though pressure is there, I need 6 equations and 6 unknowns. So I should have another equation. But calculation of these things, here rho and here v and here t is easier. So if I want, I can keep p on the left side and take all the things to the right side and calculate. Okay, but that is not a comfortable way. And this particular one method is time marching method, which made the CFD people's life so easier. Okay, so then we have got p is equal to rho.
So only variables like density, velocity, and temperature, time march, and pressure is calculated with the equation of state.
Yeah.
Okay, sir.
Yes. Okay, so we have to formulate the problem means I have to know the governing equations. Okay, governing equations, you need not worry much. The generalized governing equations are available in any data book. Okay, CFD equation and Navier-Stokes equations. Without any assumption, the complete Navier-Stokes equations will be available. Okay, so that is not a big problem. But once you understand the physics, and because these complete Navier-Stokes equations are highly complicated equations which cannot be solved by the methods that are available now. So I have to make it simplified. And for that, I have to make some assumptions based on the physics of the problem. Okay, so you have to simplify the model without laws of physics, making some assumptions. So this is very important. Okay, that you can make proper assumptions only if you understand the physics of the problem. If you don't understand the physics, I will make some assumptions so that the equations get simplified, but it may not represent your physics. You may lose your physics. Okay, so that is more important. I have to get it simplified. Suppose if I remove the density, one variable is reduced, but it can be reduced only if it is incompressible. If I am sure that the variation of density is very, very small. Okay. In the same way, if you remember in the first law of thermodynamics, conservation of energy, if you are using for boiler, when you use it for boiler, you will say the work done is negligible. And when you use the turbine, we say heat transfer is negligible. And if you use a nozzle flow problem, you will say heat transfer and workflow are not there. Work transfer and heat transfer are not there. So like that, we make some assumptions so that things get simplified. And further assumptions will make if you take Rankine cycle and across a boiler, if you take, you will neglect the change in kinetic energy, change in potential energy, work done, everything. Only heat transfer is equal to change in enthalpy. Like that, we will make. But still, we get beautiful solutions, very much accurate because they are very much small. It is like adding 1 to 100 and so much time spending to calculate 1, it's a waste of time because 100 plus 1 is there. If 1 is negligible, no problem. But if it is 1 or 0.9 or 0.95, I need not worry about it much. Am I clear about it?
Yes, sir.
Okay, so I have to make the proper assumptions. Okay, all these equations I have given, we will discuss all those things in the next class about governing equations. Okay, these are the assumptions. So we have various types of assumptions like whether it is steady or unsteady. So every assumption, actually what it will make is either it reduces the dependent variables or primitive variables, or it may reduce the independent variables. What are the independent variables? X, Y, Z, and T. Okay, if it is steady flow, T is gone. I need not have T derivatives. And if it is 2D flow, one z derivative can be eliminated. If it is 1D flow, y derivatives, z derivatives can be eliminated. Okay, in that way, I can simplify that. Okay, so whether it is steady or unsteady. So steady means dou by dou t equal to 0. And compressible or incompressible. So if it is incompressible, rho is constant. So when one dependent variable is reduced, one equation can be reduced. In the same way, viscous or inviscid. Okay, if it is inviscid, all the shear stress terms and viscous terms, all those things in the momentum equation and energy equation can be neglected. So all those lot of complexity can be reduced. In the same way, 1D, 2D, or 3D. So if it is 2D or 1D, as I told, derivatives with other independent variables can be eliminated. Okay, laminar or turbulent. Okay, so this we will discuss in the later in detail. Okay, if it is laminar, it will be simplified, and turbulent, you know that it will be very complicated. Physics will be there, and I have to know exactly how to deal with it. Okay, then subsonic or supersonic. Okay, if I have supersonic flow, then there will be shocks. There will be combination of supersonic flow and subsonic flow, and each type of flow is to be dealt in a different way in CFD, right? I cannot use the same technique that I used for solving subsonic problem, and I cannot use the same technique for supersonic problem. So when I have a shock, I have a combination of subsonic and supersonic, and how to deal with it. Okay, then force is dominant or negligible. As I told, when I have momentum equation, I have pressure force, I have shear force, and I have body force and all those things. So some of the forces, if they are negligible, I can eliminate them. And similarly, single phase or multi-phase flow. So I will have additional equations for multi-phase flow. Okay, that we will deal it later. And again, the thermal effects or density effects or free surface flow, and whether surface tension is considerable or not. These non-dimensional numbers you may be familiar. So based on that, if it is surface tension is important, then Weber number will come into picture. If free surface flow, Froude number will come into picture. If there are chemical reactions, Peclet number, Darcy number, all those things are important. Okay, so we have to see which is better. Here, Cauchy number, if it is single flow, the multi-phase flow, that number I have to be. That is because we know that every non-dimensional parameter is a ratio of two forces. Okay, if one force is negligible compared to other force, that number I need not worry about. Because finally, why I am given here non-dimensional numbers is, finally the solutions, if they are drawn with respect to non-dimensional parameters, they are more general than drawing a PT curve or pressure density curve or density temperature curve like that. If you draw, that varies from with problem to problem. But if you draw a curve between two non-dimensional numbers, then they are uh,
The trend will be same almost.
yeah, the trend will be exactly same for all the types of problems. It is like if you remember, suppose flow over a cylinder, if I take. So I have the Reynolds number versus drag coefficient. It will be something like this. Okay, so this is transition region, and this is turbulent region, and this is laminar region, like that. Okay, and but here it actually, this is rho Vd by mu, and this is drag by half rho V square into A, like this. And I have so many parameters. If I really want to, before non-dimensional dimensional analysis are getting non-dimensional numbers, and if you want to do the experiments and find out what are the effects of all the variables on the drag force. Okay, here variable is there, density is there, velocity is there, viscosity is there. Okay, and uh, dimension is there. So I have to know the effect of each variable with respect to the force. Okay, this is diameter, and drag force is different. Okay, so F I will put drag force. So the effect of all these I have to know on the forces, and also I don't know what are the interdependency. So normally what I do, I keep density constant and vary the velocity and find out the force, vary the diameter, find out the force. Like that, I have to do so many experiments and so many hundreds and thousands of graphs and plots you will get. So how to analyze that? It will be very difficult. But if I do the dimensional analysis, I am getting only Reynolds number and drag coefficient. And I will get a graph like this. And this graph is valid for whatever diameter cylinder you take, for whatever velocities you consider, for whatever fluid you take, whether it is air or liquid or water or some other mercury or some helium, whatever it is, the same graph is valid for all the things. That is the main importance for doing dimensional analysis and drawing the graphs between dimensional parameters. Okay, non-dimensional parameters. Is it clear what I am talking? Because many times people don't know why we do the dimensional analysis and what are the uses of getting non-dimensional groups. Okay, this is the main important thing. Okay, so I have to make assumptions and see what are all the main contributing things in the equations, and those things only I consider. Remaining I eliminate so that I will get the simplified equations which may be possible to solve using numerical methods or CFD. Okay, so this is a very, very important thing. But as I told, it is not just you eliminate this, you eliminate that so that the equations become simple. It's not the question of just making the equation simple, but without laws of physics. Okay, that is important. Okay, then once you do that, the next thing is I have to decide about the geometry. Okay, another thing is, as I told, the equations are same for whatever physics you take, for whatever problem in the nature you take. All these fluid flow problems in the nature are governed by same governing equations. Okay, then if same equations are there, I have to get same result. And how can I can solve different problems? So for which problem I am getting the result? How to know about it? Because I'm solving the same equations for every problem.
The pattern across different bodies is different, sir.
Yeah, the problem differs in two things. One is geometry or the flow domain, and the second is boundary conditions. Your geometry is different. Whether I'm doing the flow through a IC engine or flow through a compressor or flow through a turbine or flow or an aircraft. Okay, whatever I take, all are flows only, all are governed by governing equations only, but the geometry or the domain is different from problem to problem. Okay, so that is one of the thing which varies from problem to problem. The other thing is boundary conditions. Okay, whether it is viscous flow or laminar flow or turbulent flow or incompressible flow, for each type of flow, the boundary conditions will be different. Okay, the physics decides the boundary conditions. So I have, and so this vary from problem to problem. For each boundary, for one boundary maybe you may be knowing something, and for another boundary you may not be knowing, and for another problem you know about this boundary and all. So I have to know about the boundary conditions, and these are the two things which differ from problem to problem. So you have to be clarity about this. If your boundary condition is different, if you don't have proper physical understanding, and if you give some other boundary condition, you get the solution, but not for that problem. You are solving some unknown problem. You get the solution, but this is not the solution for the problem that you are trying to solve. Okay, so boundary condition changed means you are solving a different problem. So that you have to be clear about it. So I have to know about the geometry. Knowing the geometry in CFD is a bit tough thing. In finite element method, it's okay. Because if I want to find out what is the stress concentrations on a connecting rod or a crankshaft or something like that, okay, the domain is very much clear. The geometry of the particular component on which I am finding out the stresses is very much clear, and that is the domain. But in CFD, it is not like that. I have to decide the domain. Okay, why this is difficult? Okay, suppose I want to find out the flow over an aerofoil. Okay, so I have to find out what is the temperature distribution or pressure distribution and velocity distribution over the aerofoil. And I have flow, some uniform flow coming like this. Okay, then what is the domain? Is it the aerofoil only is the domain?
No, sir, we need to capture
No.
the wake region. We need to capture
Yeah,
the
because I have flow here. And that flow is different if I come to this point. Because the flow, it gets affected like this. Okay, so I don't know what are the conditions at this point. I know conditions only at a little bit far away from the aerofoil. So I can give the boundary condition, what is the velocity, what is the pressure, what is the temperature at far away from this. And from there, how it is varying, I have to calculate to find out what is the pressure distribution or velocity distribution of the aerofoil. I have to see how it is varying from that inlet boundary to the aerofoil. Okay, so I have to start the boundary here. And usually these are called elliptic problems. I have to have a closed domain. So it has to end somewhere. And here also where I have to take this boundary. Here also I have to be in a position to prescribe the boundary condition. I have to know how it behaves at this particular line. And how to know about it. Unless if here there will be lot of vortices and disturbance will be there. I cannot tell anything near to this. I have to go very far like this. And here afterwards, the variation in the properties are negligible with respect to x direction in the flow direction. So up to that, I have to take the boundary. And then I have to close it. I have to have something like this. And though this aerofoil is very small, I have to consider a very large domain to calculate the flow properties on that. So that is the main difficulty thing. And what is the distance I have to take? And that either you have to do a lot of numerical experiments or I have to depend on the literature. Okay, so somebody some 1 century back has solved this. He has taken so many chord lengths on the upstream and so many chord lengths on the downstream and so many lengths here and here like this. Nearly some 5 chord length I have to take here. Some 10 chord length this side and 10 chord length this side. Some 20 chord length this side. I have to take so much of domain I have to take to just get the, and if you take the whole domain, actually this aerofoil actual body that I am interested in will be very small in the whole domain. Okay, this is the way I have to decide about it. So that is the important thing in CFD compared to finite element. What is the difficulty? I have to decide about the flow domain. Okay, there are 2 types of flows. Broad classification for CFD are internal flows and external flows. So external flows means flow over bodies like airfoil or aircraft or automobile body. Okay, so like that flow over bodies like a cylinder or sphere. And internal flows flow through
pipes,
flow through pipes or
channels.
IC engines or channels, internal combustion engines. Like this, flow through some things, okay? And flow in a room, HVAC, right? If you are doing air conditioning and ventilation studies, so flow in a room like that. These are internal flows. For internal flows, actually the geometry is just like finite element method. You can confine the body domain to the geometry. In a room geometry, so you know it. Okay, so that is like that. But for external flows, the domain, you have to decide what is the domain you have to consider. And okay, once you decide about the domain, and the next is the boundary conditions. Okay, boundary conditions. There are different types of boundary conditions. One is called as Dirichlet condition. Have you heard about the boundary conditions?
Not discussed in any theory subjects yet.
Okay. So Dirichlet condition means prescribed dependent variable. If dependent variable is prescribed, as I told, inlet condition. So at the inlet, prescribing velocity, pressure, temperature, all these are Dirichlet conditions. Okay, prescribing the dependent variable. This is also called as boundary condition of first kind. Okay, so boundary condition of first kind means Dirichlet condition means prescribing of dependent variable on the boundary. I know the value of the dependent variable on this particular boundary. Even no slip condition. What do you mean by no slip condition?
Relative velocity must be zero.
Yeah, it's if there is a flow or an aerofoil, the velocity on this is zero. If it is a stationary aerofoil or flow over a flat plate. So here the velocity is equal to zero. So this is what are at stagnation points, velocity is zero. Okay, this is called as Dirichlet condition. And then the second one is what is called as Newman condition. That is prescribing the derivative of the dependent variable. This is called as boundary condition of second kind. Okay, derivative. Suppose a wall is insulated. Means, so dou T by dou X equal to 0. That is temperature is not changing, right, at that point. So if it is insulated. Or, okay, this is another thing. Okay, Dirichlet condition. Okay, if you come to heat transfer, constant temperature wall condition. Because normally there are two types of walls, either constant temperature wall or constant heat flux wall or insulated wall. Okay, constant temperature wall condition is Dirichlet type. But the Newman condition, constant heat flux boundary. Because Q is given means Ka dou T by dou X. So dou T by dou X is given. This is because K is a constant, A is a constant. If Q is given, dou T by dou X is given. Okay, this is derivative is given. And if it is insulated, this is equal to 0 because Q equal to 0, dt by dx equal to 0. So this is the way if you are given, this is called a Newman condition. As I told in the previous one, on the inlet boundary, that is Dirichlet boundary, usually. But when you come to Newman condition, exit boundary, as I told, if I have taken like this, here the dou by dou x of dependent variable is equal to 0. That is, it is remaining constant over that. That is, there is no more variation in the properties. So that is exit boundary. So exit boundary is Newman boundary. Like this. Okay, sometimes there is another one, the third one. This is called as Robin condition. This is what is called as a linear combination of first two kinds. This is called as boundary condition of third kind. So this is sometimes called it as convective boundary condition. Okay, so that is if I have a wall here, whatever is conducted here, it is convected out. It is not insulated, it is convected out. I will be given thermal conductivity of the body and convective coefficient H, right, in the flow outside. Because heat transfer problems we might have studied, it will come like this. So whatever is conducted is K dt by dx, K dot T by dou x is equal to whatever is convected is, okay, Ka dot T by dou x, Ha T minus T infinity. Okay, so this T is to be obtained. So here T is unknown. Okay, so here there is a combination. Here derivative is there and dependent variable also is there. It is a linear combination of both. If it is if it is z, if it is insulated, this will become 0. This will become Dirichlet condition. Okay, so if you know temperature, dou T by dou x will be known. It will be Newman condition. Like that, we will have a combination. This is called as convective boundary condition or boundary condition of third kind or Robin condition. Okay, so this is called as Robin condition. And there are various any other things. Sometimes we call it as okay, mixed boundary condition. Mixed boundary condition means, so up to some point the temperature may be prescribed, or up to some point heat flux may be prescribed. Then this is Dirichlet, and here it is Newman. So some boundary you are given the temperature, some boundary you are given the heat flux, then this is called as mixed boundary condition. So these are various types of boundary conditions. There are so many like periodic boundary condition or cyclic boundary condition, all those things. All these things come under one of these categories. So if you know the dependent variable, or if you know the derivative, or you know the combination, so it comes to one of them. Okay, decide about the geometry or the boundary. And okay, once you decide the boundary and boundary conditions, the next step is okay, discretize the geometry. You have to discretize the geometry. Means that is called as grid generation. As I told, what is the difference between analytical and numerical solution?
One is continuous solution and one is
This is
discretized.
continuous solution. You will be given rho as a function of x, y, z, and t, and temperature as a function of x, y, z, and t. So at any point x, y, z coordinates and time, you'll be able to find out what is rho, what is t, what is pressure, and all those things. So this is a continuous solution. And numerical solution, we get approximate solution at discrete points, which are called as nodes. So I have to get the nodes. I have to divide the geometry into number of nodes or grid. Okay, so this is called grid generation. So this is a thing next we have to do. Once I know the geometry, I have to generate the grid. Okay, there are various types of grids. So we can have what is called as fixed grid or adaptive grid. Fixed grid means same grid throughout a calculation. and grid changes during the calculations. Okay, if you use the same grid throughout the calculation, it takes more number of iterations. Adaptive grid means based on how the variables are changing, if it can change the grid by some coding you have to do anyhow for that. And based on where the dependent variables are changing more, if it automatically makes the grid fine in that positions, then it will be very fast. But coding will be difficult, but the number of iterations and the time it takes can be reduced. Okay, and this, whether this is or that. So we have various methods of grid generation, like algebraic grid generation, or conformal transformation, or conformal mapping, or grid generation using partial differential equations. Okay, so these are various methods, and one more thing. Okay, the like structured grid and unstructured grid. Okay, this is important. This is the first thing you have to understand. Structured grid and unstructured grid. Okay, what do we mean by structured grid? So if I have a grid like this, okay, so here I equal to 1 to m, and here j equal to 1 to n, like that. So if any grid point can be identified by number of grid lines, it can be given some 2, 3. That is second horizontal line and third vertical line or something like that. Okay, I can identify each node based on the grid lines, numbers of grid lines. This is called a structured grid. And unstructured grid, we cannot do like that. So it can be a triangular grid or rectangular grid, whatever it is, but it is completely complicated. So you cannot identify the grids based on the grid lines. That is unstructured grid. Okay. Okay, then within the structured or unstructured grid, you can have fixed grid or adaptive grid. And structured fixed grid can be generated using algebraic or conformal mapping, or grid generation using partial differential equations. And again, based on this, we have elliptic grid generations, parabolic grid generation, based on the type of equation you use, hyperbolic grid generation. It is depends on partial differential equations which are used to generate the grid. If it is elliptic type, we call it as elliptic grid generation, or parabolic grid generation, or hyperbolic grid generation. So these are various grid generation techniques. And up to grid generation, we call it as pre-processing. There are 3 steps in CFD. One is pre-processing, and then processing. Means solving the partial differential equations at those grid points. And I find out the values at all those grid points. This is called as processing. And once I know all the values at all the grid points, so I have only numbers by seeing it, which we cannot understand, then we what is called as post-processing. Means representing the results in picturesque manner. It can be contours, it can be XY graphs, it can be velocity vector plots, or animations. Okay, like that we can have various methods of post-processing. Okay, these are the main thing: pre-processing, processing, post-processing. Pre-processing is up to grid generation. Once the grid is generated, the pre-processing is over. Then what is the method of solving partial differential equations, which we are going to study? Okay, so various types of schemes for various types of equations. That is called as processing. And once I get the results, all the values at all the nodes and how we present them, right? The results is called as the post processing. Okay, so these are the 3 steps. Okay, decide about the geometry, flow configuration. See, external flow or an aerofoil. You see here what is the domain you have taken and what is the body it is. So much of domain I have to consider. And internal flows, okay, a fixed body like this. And so internal flow, it is like flow in an automobile, right? So if you want to know how the air conditioner in the automobile works and what is the temperature distribution, what is the comfort levels of the persons, and flow through a nozzle, right? And okay, all these things, these are post-processing results. This is external flow, this is internal flow. And so even choosing the domain, if I have a flow through number of slots like this, okay, and here, because of the symmetry, I need not take the whole domain here. Only a sector of the domain I can take because that gets repeated symmetry because of the symmetry. Okay, only if I take the sector, that is enough. So it reduces a lot of load on the computer. And boundary conditions, as I told, Dirichlet, Newman, Robin condition, mixed conditions like this. And we have solid walls, inlets, outflows, symmetry, cyclic and periodic, free surface or interfaces, far field boundary conditions like that. So if you have flow over a cylinder like thing, I have this much of domain, right? So this is exit boundary, this is far boundary, and this is the inlet boundary where I have Dirichlet condition here, Newman condition here like that. So here also you can have different boundary conditions. So suppose if I have a pipe flow, here on the wall, I will have no slip boundary condition. That is the Dirichlet condition. And again exit, I have Newman condition like that. So if I have flow through a cascade, so flow through a cascade also, though I know I want the values only in this region, but because I know the inlet conditions here, I have to take the boundary like this and exit boundary here. This. So this is the way I have to take. And cascade is actually number of aerofoils like that, but because the flow through 2 aerofoils, if I take, the same thing gets repeated that side or this side. So these boundaries are called as periodic boundaries. Okay, because periodically they occur after the next the 2 blades like that. Then discretizing the geometry, structured grid and unstructured grids. You can see here, this is structured grid, this is structured grid like that. But if you see, this is completely unstructured grid. And I will talk about, so show adaptive grid also. These are hybrid grids. Some part this is structured and this part is unstructured like that. And near the boundary, usually we take structured grid, and away from the boundary, we take unstructured grid. And the adaptive grid, suppose if I want to find out the flow distribution of this particular body, and initially I have taken an unstructured grid like this, and this gives this type of result. But actually, there are some sharp flows here, and if I want to exactly capture them, I have to have proper grid. So here, once I have the rough calculation, I can see there are lot of gradients here. These are constant Mach number contours or pressure contours. So here there is a lot of pressure changes there. So that's why I know that here there is something happening. I want to have more number of grid points here. So if I have an adaptive grid, what happens is I will get a grid like this. Okay, after every few iterations, it changes its grid pattern in such a way that it will have more number of grid points where the properties are varying. So this is actually, if you see this, by seeing the grid itself, you can understand what type of flow you are going to get. So these are shocks actually. So you can see this is the result. Okay, previously this is the way, but now it is fine result where I can find out exactly where the shock comes. These are oblique shocks. These are captured exactly. That is adaptive grid. And for method of grid generation, you have algebraic methods, PDE methods, elliptic, hyperbolic, and parabolic, conformal mapping. These things I told. And unstructured grid generation also, it has some steps like domain nodalization, domain triangulation. And in triangulation, I have advancing front method and Delaney method. These things we are going to discuss later. Just I'm giving the terminology. Okay, so nodalization I have to do because the complete domain is to be nodalized. I have to find out some nodes and then I have to triangulate them. So there are various methods like domain triangulation, advancing friend method. By triangle by triangle, it produces like that. And then what type of, for processing, what type of methods I can use? I can use finite difference methods, finite element methods, and finite volume methods, FDM, FEM, and FPM. And so how to solve it based on it is elliptic, parabolic, or hyperbolic. You have different methods are available. So classification is hyperbolic, parabolic, elliptic. And how you discretize that, again we have a chapter to discretize the equations. It just it is overview only. And how to solve them using explicit methods or implicit methods, and how to find out the stability. I have to check the stability whether my particular scheme is stable or not. Okay, just I am showing these are not necessary now. So these are various schemes for different types of problems. Okay, the various properties of numerical methods like consistency, stability, convergence, conservation, boundedness. So for each scheme, I have to find out these characters, and then based on that, which scheme is suitable for a particular problem, I have to decide. Okay, then the post-processing is like this. If you want streamline plots, you can get like this. If you have XY plots, you can get like this. If you have velocity vector plots, you can get like this. And flooded contours by grayscale. Based on the colors, you can find out where there is a high pressure or high velocity or low velocity. And these are like color plots. Here you will have the index. So here red color is high value and blue color is the lowest value. Velocity vector plot, pressure contours, scatter plots. Here, various circles based on the size of the circle, and you can find out whether value is high or low. And mesh plots, and you can have composite plots. Like some part you can have velocity vector, some part you can have grid, some part you can have contour like that. These are called composite plots. And you can have animations, which we have seen already. So like this, we have to present it. Then I have the validation you have to do. And once you do the validation, and then you can do the further calculations for unknown regions or unknown conditions. Then you can publish the result. Okay, so this is about the whole thing. And what are the job scopes? Okay, various companies that you, if you are expert in CFD, you can be absorbed in those companies. Okay, so we'll close here. Let's love people and use material things instead of loving material things and using people. Okay, so that's what people do in a reverse way. And they love material things and use people. But we have to love the people and use material things. And you are not the same person you were 1 hour ago, because all junk, whatever I have given you, it is there in your head in some of it. So whatever you were one hour ago, you are not the same person. And you are not likely be the same person 1 hour from now. Okay. Next hour also you are going to change. So change is natural. Okay, small story will, I think, we'll complete this. Okay, Thanksgiving Day was near. The first grade teacher gave her class a fun assignment to draw a picture of something for which they were thankful. And most of the class might be considered economically disadvantaged, but still many could celebrate the holiday with turkey and the other traditional goodies of the season. And these the teacher thought would be the subjects of most of her students' art. And they have drawn different things what they are going to get in on a Thanksgiving Day. So such things they have drawn. But there is one student, Douglas, made different kind of picture. Douglas was different kind of boy. He was the teacher's true child of misery, frail and unhappy. As other children played in recess, Douglas was likely to stand close by her side, and one could only guess at the pain Douglas felt behind those sad eyes. Yes, the picture was different. When asked to draw a picture of something for which he was thankful, he drew a hand. Nothing else, just an empty hand. His abstract image captured the imagination of his peers. Whose hand could it be? One child guessed it was the hand of a farmer because farmers raise turkeys. And another suggested a police officer because the police protect and care for people. Still, the others guessed it was the hand of God, for God feeds us. And so the discussion went until the teacher almost forgot the young artist himself. And when the children had gone on to their assignments, she paused at Douglas's desk, bent down, and asked him whose hand it was. And the little boy looked away and muttered, "It's yours, teacher." She recalled the times she had taken his hand and walked with him here or there as she had the other students. How often had she said, "Take my hand, Douglas, we will go outside. Or let me show you how to hold your pencil. Or let's do this together." And Douglas was most thankful for his teacher's hand. Brushing aside a tear, she went on with her work. This story speaks of more than thankfulness. It says something about teachers teaching and parents parenting and friends showing friendship and how much it means to the Douglases of the world. They might not always say thanks, but they will remember the hand that reaches out. Keep reaching out because you may help pull someone out of darkness and guide them into the light. Okay, thank you very much. Any questions? So today we have gone through the whole CFD process. So we have to select a real world problem and we have to understand the physics, and then we have to see the feasibility and resources that are needed, whether they are available or not. Then we have to find out what are the governing equations, and then I have to make proper assumptions and simplify the equations without loss of physics. Then decide about the geometry of the problem, whether it is internal or external flow, and what are the boundaries or the flow domain to be considered. And then I have to find out the boundary conditions. And after that, I have to generate the grid. And up to grid generation, as I told, it is pre-processing. Then I have to solve the equations, the governing equations, using some of the scheme based on the type of governing equations I have got. I have to use proper scheme and which solves, that is called as processing. And I got the result at various points or various points in the domain, and that I have to do the post processing to present them in XY graphs or contour plots or velocity vector plots or anything, so that the physics can be clearly demonstrated. And after that, I have to do the validation. I have to show that my code works well. Then I have to get the results for the unknown cases, and then I can publish the results. Okay, this is the way we solve a CFD problem. Any questions? Any questions? Are people there?
No questions.
Okay, then as I told, we will have the test. I will inform you if it is LMS is available. We will have at 6 o'clock. Otherwise, I will create Google Classroom, and if you join there, I will. We will have the test tomorrow. Okay, if there are no more questions, so I will start recording.
Hello.